Okay, welcome. Okay, welcome to everybody. This session, the last for this long day, is devoted to quality of service. Unfortunately, the first speaker would have to speak about what essentially Grid thinks about quality of service is missing. I apologize for that. He couldn't make it. Nonetheless, we have two interesting presentations. As you know, quality of service is not just on the network. To really have quality of service, you have to have a transport protocol up to what you want to do, and an operating system that supports this transport protocol and so on. So the first talk, held by Sven Hubik, will be about how to achieve high performance with a transport protocol. Sven is a researcher in Česnet, in the Czech Republic. And after that, we will have the hands-on experience on quality of service provided by the GIANT network, the European network, by Nicolas Simard. So we have transport protocols and then a real experience of what's going on the quality of service in the European environment. Sven.
Introduction. Well, as Mauro said, I am from Česnet, which is an operator of the National Research and Educational Network in Czech Republic. And I would like to talk about some issues which should be considered when we want to reliably achieve high performance in long-distance, high-speed networks or long-fat networks, named so because of a high possible volume of the outstanding data which can be at some time sent by the sender being in the network but not yet acknowledged by the receiver. This high volume of outstanding data can cause some performance problems. Well, it turns out that the performance observed by the user between two end hosts is not only dependent on the physical characteristics of the network itself, but it's a result of complex interaction of all components along the communication path, that is beginning from the application over the operating system, the network adapter, communication protocols, and the network itself. If some of these components is slow or misconfigured, or there is some bad interaction between some of these components, then the resulting performance can be much worse than what you might expect from the speed of the physical network. And as many advanced users, those who require high performance from the network, are now using Linux PCs, not all, but many of them, we decided to concentrate in the first phase on end-to-end performance when using Linux PCs. And given that, it seems that there are three primary problem areas. The first is TCP window configuration, how big it should be and how we should configure it. Second is the interaction between operating system and network adapter. And the third is interaction between SSH, popular protocol for secure data transfer, and TCP. So let's first look at TCP window configuration. You probably know that when we want to achieve good performance over long-distance, high-speed network, then we need to increase the size of TCP buffers from the usual default size of 64 kilobytes in most operating systems. And you can do it either manually for one application by a system call called from the application, or manually for all applications by setting system default for all newly opened connections. Or you can use some of the tools for semi-automatic buffer windows configurations, like dynamic right sizing or what work around the daemon and such things. In any case, one of the two things happens. Either syscontrol command is called to set operating system default, or setsoc system call is called to change buffers for a particular socket. And the tricky thing is that the Linux kernel includes a sort of arithmetics which is applied to the values which is specified in syscontrol default call or setsoc call, so that the resulting buffer size and window size is different from what you specify. You might have noticed that when you use iperf for throughput measurement and you say that you want, say, 1 megabyte window, it says that you have 2 megabyte window. But in fact, iperf is still not true because it's more complicated. It says that you have 2 megabytes window because the value which you specified is internally doubled by 2, which is a complicated legacy of all 16-bit arithmetics in all TCP stacks. And then this value, which is returned by getSocOpt, which is what says iperf, is a subject of further processing where part of this value is taken away as an application buffer and only the rest can be used for TCP window. And even this rest is dynamically moderated during connection runtime to prevent sudden bursts from the sender. So this kind of arithmetics should be considered when we want to do measurements with reproducible results. So given that we managed to specify TCP window which we wanted, we should consider interaction between the IP layer and the network interface card. When the application has lots of data to send, and when TCP sender has a big window, then the application can send a large chunk of data submitted to be sent to the network at once. But the network interface card can send out packets only at the speed of the physical network, which is, for example, 1 gigabit per second. So there's a transmission queue between IP layer and network interface card to store packets until the network interface card can send them out. And when this queue fills up, the process gets signal and the operating system switches context to another process because it makes no sense to keep context for this process when it can't send any more packets. This is no problem at all as long as the transmission queue is large enough to supply fresh packets to network interface card for the period for which context can be switched to another process. With standard Linux system timer running at 100 Hz, you can easily calculate that you need a transmission queue of that can fit at least 833 packets for gigabit Ethernet adapter. The default size is 100 packets, so it's a good idea to use ifconfig command with takesqrun parameter to increase the size of takesqrun, of the transmission queue. And effect might have is illustrated in this figure, which shows throughput which we achieved on one of our testing paths over Géant. It's a throughput depending on TCP window size, and you may see that beginning with 2 megabyte window, throughput begin to decrease, and when we increase the transmission queue size, the throughput improved significantly. However, for really big windows, it was still decreasing, which has several reasons, and the most important of them seems to be overfilling of route to queues. TCP is so-called self-clocking, in a sense that the sender can send out packets only at the rate at which acknowledgements are coming from the receiver, and in this way it adjusts automatically to available bandwidth at the bottleneck link. However, this doesn't stop TCP sender from still increasing its congestion window using additive increase, multiplicative decrease algorithm until the volume of outstanding data is so big that it begins to accumulate in router queues. All TCP connections do that, and in some point router queues are filled up to some extent, and due to natural fluctuations of user traffic, it can happen that some loss occurs, and consequently TCP sender had to slow down and throughput decreases. There's a sort of TCP called Vegas, which tries to check if the throughput during the last round trip time corresponds to expected throughput from the current outstanding window, and if not, then it deduces that reason is that queues are filling up, and it stops increasing congestion window. It turns out that TCP Vegas has some problems with fairness, and in some cases it actually produces lower throughput than standard Reno TCP. So it hasn't been much adopted, but it seems that there is another way to find out when router queues are beginning to fill, which is checking RTT. Sorry. This picture shows round-trip time development of one connection. The lower bound is round-trip time on empty network. In our case, it was some 45 milliseconds. And the peaks are caused by fluctuations of data in router queues. In this case, it topped at some 110 milliseconds. And you may assume that if we manage to process round-trip time development in a proper way, we can predict when it is useful to stop increasing congestion window, and in that case we might prevent losses and improve throughput. Actually, we are working on a modification of TCP which will use this phenomenon, but this is still work in progress, and so I will not go in further detail. I will answer the questions maybe later, but what I would like to mention is another performance problem. Linux kernel has a TCP cache which remembers some parameters for individual destination IP addresses, and one of them is ss-trash, which is a limit of congestion window when the TCP connection switches from the exponential increase of the slow start phase to linear increase of the congestion avoidance phase. And it can happen that one connection to some destination goes particularly bad, and ss-trash is significantly decreased due to multiple losses. It is remembered in TCP cache, and the subsequent connection to the same destination uses this low ss-trash value as its initial value, which is what happened in connection whose outstanding window development is shown in this picture, and you can see that the exponential increase stopped suddenly without the usual peak, and then it increased only very slowly during congestion avoidance phase, and that's why throughput was locked at low value given by congestion window near the SS threshold value. Fortunately, this performance problem can be easily rectified by clearing TCP cache using this command writing 1 to one of the Broad's file system variables. So it may seem that until we have a proper window auto configuration and moderation which will ensure that the window is large enough, but also ensure that it doesn't grow too large to overflow router queues, we might achieve the best performance over some network path when we find out what is available bandwidth there and adjust TCP window correspondingly. One way to do it is to use iPerf, which, however, stresses network with full speed data stream. And another way is to use pathload, which is currently, as far as I know, the only publicly available tool for available bandwidth estimation without using brute force data stream. There are more such tools in development, but this one is only publicly available. We tried to do quite a lot of tests with it. It seems that, unfortunately, it isn't much reliable. In our experience, in about 1/4 of cases, it produced unrealistically low indication of throughput. In some 7%, it indicated unrealistically high throughput, and the rest looked realistically, given the path which we used for measurement. But sometimes the indicated range was too wide, like 150 megabits, so it wasn't much useful. And we also tried to use path rate, which should estimate installed bandwidth of the bottleneck link. And we found that it also produces lots of fluctuations and didn't prove to be much useful. I have some pictures from those measurements. This line up there is path rate, so you see lots of fluctuations. It wasn't much useful. This red line is UDP iPerf running at some 950 megabits per second. These flat sections were probably limited by end host performance, and moreover, it's not for certain that there was really such available bandwidth, because UDP could stress other traffic which was mostly TCP. These lines in the bottom are iPerfs with different TCP iPerfs with different window sizes. What we did was that we repeated measurement with each window size several times, and as we expected, it turned out that as the window size increased above the wire pipe capacity, that is pipe capacity not including the router queues, results from different iPerf measurements with the same window size were rather different. There were lots of fluctuations, which was a consequence of different loss patterns during different rounds of measurements. So it seems that we may use this occurrence of fluctuations of results in iPerf measurements as an indication that we have reached available bandwidth. And but this is quite brute force kind of measurement because we need to repeat the test many times and also it takes lots of time. Here the red line is pass load, which is somewhere between TCP and UDP iPerf, which might be realistic but also can be a matter of luck because as we encountered on another pass, here pass load consistently indicated much lower throughput than it was realistic. So so far it hasn't proved to be much useful tool. Well, now I would like to mention one important performance problem in SSH. It's good when we manage to set up TCP so that we achieve high performance using iPerf, but people are not transferring their files using iPerf, they are using file transfer tools like SCP, and SCP is based on SSH, and it turns out that there is some performance problem. We, for example, used SCP to transfer a high volume of data on our testing path from Sesnet to Uninet in Norway, and we have achieved very low throughput of 10 megabits per second. This picture shows development of this connection obtained from TCP trace and export. The green line are acknowledgement numbers from the receiver, and the white dots are sequence numbers from the sender, and as you can see the sequence numbers were very close to acknowledgement numbers, so the sender wasn't able to utilize the receiver advertised window, so there was clearly some problem on the sender side. In such a case, some people blame blindly CPU load. They say, well, SSH does encryption and decryption, and therefore it runs much slower than plain TCP. Well, we checked CPU load, and it was about 9%. So, what was the problem? For encryption purposes, SSH protocol packs data in blocks. Each block is by default 32 kilobytes long, and these blocks are acknowledged at the application level. And for these acknowledgements, SSH keeps its own internal window above the TCP window. And this internal window is by default 4 blocks big, which is 128 kilobytes, which is the limit of data which can be transferred over any round trip time. And obviously over a long distance network it limits throughput to low levels. So what we did was that we patched SSH so that the internal window could be adjusted, and this picture shows dependence of throughput over the internal SSH window. Here is throughput of about 10 megabits per second with original SSH, and with bigger internal window we achieved throughput of up to 180 megabits per second over the same network path. But obviously the CPU load increased accordingly. With this throughput, CPU was not doing anything else than just working for SSH. But the CPU load wasn't the primary problem of the initial low throughput. And here you can see a development of connection with SSH window increased to 40 blocks, where you can see that the sender was pretty much able to utilize the receive advertised window. And to conclude, you can say that large TCP windows require also other configuration tasks to be done, such as caring about TCP cache and other things to achieve good performance. Second, any sort of auto configuration or window moderation which we will attempt to use should not only take care that the TCP window is large enough so that it doesn't block throughput, should also take care that it doesn't grow too large to overfill router queues. Third, there appears to be a performance problem in SSH, which was revealed when it is used over long distance networks, and which must be resolved at the application level. And I would say that given all this, we can say that influence of operating system configuration and of some implementation specific features which are present in Linux and probably in other operating systems may have sometimes a bigger influence on performance than some amendments in congestion control proposed in some internal drafts. So we should take care of them. Thank you for your attention.
Questions?
Two questions. One, for SCP, do you actually have to recompile SSH, or is there some runtime command line parameter that you can use to increase the internal buffer?
For our tests, we had to recompile it. There is a compiler time constant which specifies the internal window size, but I think that it's quite easy to make it runtime configurable. Shouldn't be a big problem.
Okay. And the second question was from earlier in the presentation. You said, well, TCP must be overrunning router buffers. Mm-hmm. Did you actually see congestion in the routers on some particular link and actually see buffers? Because if you had big fat connection with gigabit Ethernet, unless the links are congested, you should never see any packets piling up in the router queues.
We didn't look at router queues, but we observed connection development by TCP dump run on a third machine so that we didn't lose any packets, and we observed loss patterns. So it was the method which we used, and when window size increased above what we could compute as a wire pipe capacity, then and above that using router queue memory, then lots of losses occurred. But we didn't look physically at the router queue memory.
So it could have been congestion loss, router queues, or it could have been corruption loss for all we know.
What
that
kind of corruption was?
Corrupted.
It could be, but I doubt that you might have so much corrupted packets. It doesn't happen in such room.
Where do you think the bottleneck was?
I beg your pardon?
Where do you think the bottleneck link was that was causing this queuing?
Well, I don't know, because it wasn't our international link, which is from our network to the next hop. It had to be somewhere further away. I don't know at what hop it was.
Still something to research on.
Yeah. One other thing, I know that Linux 2.4 does do some auto-tuning of its buffers.
Yes,
were you able to play with that at all, and was it helpful or effective?
Well, it is mostly effective for preventing sudden bursts from the sender, like when the sender stops to send data for some time, and now all of a sudden it wants to send a big amount of data, and without this moderation, big bursts can be sent to the network and can cause losses, and this effect is suppressed by auto configuration or moderation, which is present in Linux. And it is on both sides, on the sender and the receiver as well. The receiver advertised window actually is initially small, and it grows to the size which you specify. It is data driven. As data coming from the sender, then the receiver window comes up. But unfortunately, then it stays flat even if no data are coming from the sender, which is, as I said, unfortunate, because if it can drop down, it could be one of the ways to better suppress bursts from the sender and prevent losses.
Are you planning to test other implementation as well, not only Linux system?
Okay, we are considering that. We have to think about what platform should come next. Probably Windows are, as for the large of user base, the second one we should look at, but actually I'm not much keen at debugging Windows TCP, so maybe that
BSD or something?
BSD seems to be a good candidate. But I'm not a BSD expert. From what I heard from BSD people, they told me that it's TCP is pretty much as a standard Rhino TCP. There's no such peculiarities like in Linux TCP.
That's correct.
Did you try different transmission speeds? I mean, different link, for example, 100 meg, then 500 meg connection, and then more. Just for the applications, because I know one day we've been doing similar tests, and it looked like, for example, the path rate was the best one, was the most accurate for links about 100, 155 meg, and it was really inaccurate for 10 meg links, for example. So depending on the condition, different applications might perform completely differently. For example, we had another measurement tools like C-Link, and I'm not sure whether we tested path load, but there are 4 different things that we tested, and it really depends on the local conditions, whether it was switch network, for example, whether there was ATM network, whether there was fast or slow link. So this all affects. So I would tend not to generalize or like these applications.
There have been a couple of works comparing different tools for installed and bandwidth, installed and available bandwidth estimations. Maybe that you did one of those. I'm not sure, but we didn't try to repeat this work of comparison of all the tools. We did some laboratory tests on slower speed, on 100 megabits per second with passload, injecting some artificial traffic to emulate available bandwidth, and it worked very good. But it was just a 2-hop network emulated, and so
we're exactly doing the same stuff, but on different configurations. So if it was enough to put Ethernet switch in between 2 routers. It was enough to put Ethernet switch between 2 routers, and the measurements were completely different. So, I mean, that's the whole area for research.
I know that it can happen. I read some papers about comparison of these tools. Well, we didn't want to explore all of them. We liked passload because it is supposed to estimate available bandwidth. That's why we looked at this tool, and we look how it behaved on a couple of network paths. So I didn't say that it could be generalized. I said that in that one case, when it looked realistic, it could be just a matter of case, because in other cases it looked pretty bad. So at least my internal conclusion is that puzzle is not reliable to be trusted in all network conditions.
Any other question? Yes.
Did you use a copper card or a light card, and what NIC card you used?
I think that most cases it was optical card from Intel Pro 1000.
I have a last question. Do you think that using IPv6 will change this result?
I'm not sure if there are some mechanisms in IPv6 which can help resolve these issues, because they are mostly in upper layers in TCP and in application layers. So I think that it's not fundamentally different.
Let's thanks then again. The next speaker is Nicolas Simard. He works for Dante, which is the private organization managing the European Research Network. He is responsible, among other things, of the implementation of quality of service on GARR.